Hello and welcome to this fourth session on symmetry in chemistry. Last time we were looking at some of the most symmetrical molecules, molecules with platonic symmetry. But in fact today we're going to see, in a way, some even higher symmetry because we're going to be going up to infinite fold axes and indeed systems that can have infinite numbers of axes. And really this is all about linear molecules. So on the screen at the moment, on the top there, we've got a space-filling structure of carbon dioxide, linear molecule, 180-degree bond angle. And beneath that, we've got the molecule N2O, dinitrogen monoxide, also known as nitrous oxide. And this is rather an odd structure because normally when you have two atoms of one type and a third different type of atom in a triatomic molecule, normally the odd atom is in the middle, thinking of SO2, H2O, F2O. But in this case, the odd atom, oxygen, is not in the middle. It's quite curious this because we've got these two resonance forms of nitrous oxide beneath here, and in fact, if you look at the structure on the right-hand side, you see this is actually isoelectronic with the carbon dioxide molecule. So we've got that central atom, each with two double bonds in this linear arrangement, and you can see we've got a charge separation there with a plus on the N and a minus on the outside end. So that central end, which has got the plus on, having lost one of its 5 valence electrons, that gives it a carbon structure, 4 electrons in its outer shell, and likewise the nitrogen on the left, having gained an electron from the other nitrogen, now has 6 electrons in the outer shell, a bit like oxygen, hence this kind of isoelectronic relationship. And so you see what both these molecules have in common is that along the molecular axis on which we see the bonds, you can rotate the molecule any angle and it's left unchanged. So that's an infinite fold rotation axis. And in fact we see that CO2 has even higher symmetry than N2O because of its symmetry along the molecule with the odd atom in the centre. So I pose this question here: what additional rotational symmetry does CO2 have as a result of that? So you could pause it, have a quick think about it, and I'll come back with that on the next slide. So on the carbon dioxide structure, we also have, we can have a plane perpendicular to the molecule, bisecting the molecule, and also with the two atoms on the end being equivalent, we've also got C2 axes, which are perpendicular to the principal axis. And in fact, we've got an infinite number of those C2 axes, certainly from the point of view of that space-filling model we were looking at. But then we might question that, because if you look at this molecule, this model of carbon dioxide on the right here, if you think about which p orbitals are involved, if we define, let's say, the z-axis as being the principal axis, so on the z-axis, the p orbital there, if you like, can be involved in sigma bonding, but the px and the py orbitals are perpendicular to each other, and that kind of implies that the two pi bonds in the CO2 molecule are perpendicular to each other, and that's represented in this molecule here. So, I mean, if that were the case, you might think the symmetry is much less. Maybe it's not dihedral at all. So that's an interesting question. But it turns out that these molecules actually have their pi bonding delocalized around the molecule, so it's a kind of cylindrical symmetry. So perhaps slightly mysterious why it forms this cylindrical symmetry, but I suppose if you think about the molecule in isolation, clearly the nuclear coordinates, we've got them fixed in a line, and that defines our z-axis, but really we've got nothing else really defining the x and y axes. There certainly aren't any other atoms involved. So how do we decide what our x and y axes are? So in a sense, if our axes are not being fixed by other atoms, and we're free to choose those axes, then in a way they needn't be so defined in the molecule, and so we wouldn't have to have orientations of pi bonds like they are in the picture, but they can just, as I say, delocalize all around cylindrically. And so given that, we have an infinite number of dihedral C2 axes perpendicular to the principal axis, which accompany the infinite fold rotation. And so actually this is the pattern that we see in dihedral symmetry, isn't it? When you have a Cn axis as the principal axis in a dihedral molecule, then you have n of the perpendicular C2 axes. And so actually having an infinite number of C2 axes is consistent with the molecule being dihedral. and so it gets this label here, d infinity h, and so d being for dihedral, infinite for the infinite fold rotation, and h reflecting the fact that you've got this mirror plane perpendicular to the principal axis. And of course, in addition to that, we could have improper rotations. So obviously the molecule's got a centre of symmetry, I, and of course that's the same as S2. I suppose you could argue that the horizontal mirror plane is the same as S1, and likewise you can have improper rotations around any angle because you've got that mirror plane halfway along the molecule, perpendicular to the molecule, and of course you can rotate the molecule any angle. So rotating the molecule any angle, then reflecting in that perpendicular mirror plane, it's always going to return the molecule to its original state. So we have an infinite number of these improper rotations as well. And in addition to that, if we consider mirror planes which are in the axis, which actually hold the principal axis, we've got an infinite number of those as well. We can orient them any way we like. So yeah, really a lot of symmetry in this molecule. So looking at the slightly less symmetrical case of N2O, we still have this infinite rotation symmetry around the principal axis, but we no longer have the perpendicular C2 axes. We've no longer got the perpendicular mirror plane, the sigma h. So here we are. I just thought I'd mention here that one use of N2O that we come across is in so-called gas and air. So this is something which is commonly given to women during childbirth. 50% N2O, 50% oxygen. So it's got this sort of anesthetic effect, pain relief. But yes, so we lack the mirror plane, so we certainly don't get all the improper rotations that we get in carbon dioxide. But we do still have the infinite number of mirror planes that hold the principal axis. And since all those mirror planes that hold the principal axis are not bisecting any atoms, we're going to give the subscript V. If they'd bisected atoms, we would have given it a D, but doesn't bisect, so we give it a V, and so this really is how we get the name of this symmetry class, C infinity V. So C infinity denoting the infinite fold rotation axis, and V for these infinite number of symmetry planes running along that axis. Now, in fact, we could look at something even more symmetrical now, which would be an isolated hydrogen atom. And so we can treat an isolated atom, so I say hydrogen, actually we can say the same thing for any atom. We can treat it as a sphere, which we'd call isotropic, which means the same in all directions. And so looking at the picture there as it's drawn, it looks like it might be d infinity h. It just kind of looks like we've got a principal axis, infinite fold rotation, and we can have an infinite number of perpendicular C2 axes. But the way the picture is drawn there is slightly confusing. In fact, it is a higher symmetry. And the reason it's slightly confusing is that with all those lines of latitude and longitude drawn on the sphere, it kind of draws our attention to a single principal axis. But of course, a sphere doesn't have a single principal axis, because any point on the sphere can be connected to the point on the opposite side, where you can put an axis that goes through the centre of the sphere, and that also will be an infinite fold axis of rotation. So rather than just having an infinite fold axis of rotation, we've got an infinite number of infinite fold axes of rotation. And in addition to that, we've got we've got an infinite number of infinite fold axes of improper rotation. And so that implies each of them will have their own perpendicular mirror plane, and they're the mirror planes that hold the axes. So we just got infinities all over the place. And in fact, an isolated atom, or in this case, if you like, an isolated hydrogen atom, is in fact the most possible thing you can have, the most symmetrical possible thing you can have in three-dimensional space. And in fact, on this slide, I'm sort of slightly jumping ahead here, because there's some interesting things we can say about atomic orbitals that can link up with some of our ideas about molecular orbitals as well. And so first off, I'm just going to make the general point that, strictly speaking, atomic orbitals are only really absolutely valid for hydrogen. It's from the hydrogen atom that we derive the atomic orbitals. So that model assumes there's just a single electron being attracted to a nucleus. And so in a multi-electron atom, of course, you've got electron-electron interactions as well. So really it's a lot more complicated, but we do base that multi-electron model on the hydrogen atom orbitals. That's our so-called orbital approximation. And what's very interesting is to look at the shapes of our atomic orbitals within the wider context of the spherical symmetry in which they find themselves. And we see some quite interesting relationships. And so I ask the question here, what symmetry operation is possible in s and d orbitals but not in p and f? And so we're going to consider all the symmetries of a sphere and look at some of these orbitals in particular. So you can see the s orbital there, that's on the bottom right, and you can see that the d orbital is on the top left. We've got p on the bottom left, and f, in fact, that is on the top right. So you might pause the video and think about this for a minute. There's something that the s and the d orbitals have in common. There's a certain aspect of symmetry there that we don't find in the p and the f. And this is reflection through the origins, like centre of origin, centre of symmetry. So this is the symmetry of the orbital under the operation I, reflecting through the centre. So in the s orbital and the d orbital, the lobes reflect through and the phases are preserved. So that's what the colours are in these pictures. So we might take blue to be positive phase and red to be negative phase. The phase, remember, just being looking at the wave function, if you're considering it to be the positive part of a wave, like a crest, versus a negative part of the wave, the trough. And so those two orbitals there have this symmetry for the I symmetry. But when you consider the p and the f orbitals, they don't have this symmetry, although what we do find is that the lobes, they do reflect into each other's positions, but the phases are just reversed. And so this is there's a kind of oddness about this symmetry, and these are regarded as odd parity. And the odd and even parity that relate to this reflection through the origin, they're often given the labels G and U for gerade and ungerade, which I think is German for even and odd, respectively, referring to these parities. So it's a very, very simple sort of an operation, this, reflecting through the origin. And of course this is normally a symmetry element which is permissible in a symmetrical atom. So we're just looking at the orbitals within this context. And it's also interesting going on to look in terms of nodal planes. And so this will be a plane in which there is no electron density to be found in the wave function. And this is because the wave function might be moving from a positive phase to a negative phase. So clearly it's got to go through 0 somewhere, and that 0 is a nodal point. And we tend to find these nodal points often are kind of collected in planes. So the most obvious one perhaps is like in a p orbital with your blue and the red lobes. Obviously you can think of a kind of mirror reflecting one lobe into the other, and on that mirror plane there will be no electron density. So that mirror plane might reflect these sort of axes, let's say in the molecule where the wave function is going through 0. And it's interesting to count up these nodal planes. So there are no nodal planes within the s orbital. One nodal plane sort of bisecting the p orbital. Then when you get to the d orbital there, you can see with the lobes, admittedly the dz squared looks a bit different. I mean, it's still consistent with this, but with our kind of regular looking d orbital there, we can see that we've got a pair of these planes at 90 degrees to each other, which are nodal planes at which the wave function is 0. And you can see, if you consider the d orbital to be in a plane, then when you add, as it were, another dimension to that plane and get yourself up to an f orbital, then you find there is yet another nodal plane. So you can see that in in the f orbital there, as well as the two planes that you can put into one of these kind of sheets in the top of the bottom. You've also got the plane that sort of bisects the two sheets as they appear. So we've got 3 nodal planes for F. And there's actually quite interesting relationships here, because of course S, P, D and F are subshells, and subshells really is just our way of describing orbital angular momentum states. This is what the Schrödinger equation gives us. And we get these quantum numbers, and of course the letters S, P, D and F are just kind of historical hangovers. What's really going on in the subshells, these are the 0, 1, 2, 3 quantum numbers for the orbital angular momentum quantum number. And one thing that's consistent with this orbital angular momentum is the fact that we get this sort of increasing curvature. So the more nodes you've got in the wave function, the more you have to kind of bend the wave function to keep crossing through the axes and creating all these nodes. But we do see a kind of coincidence here, don't we? So on the one hand, we've got these nodal planes looking at the symmetry of the orbitals, and on the other hand, we've got these quantum numbers which we find dropping out of the Schrödinger equation, and they're the same values. And this takes us through to quite a deep kind of truth here, that ultimately when you're talking about angular momentum, especially in this kind of quantized sense in the atom, you're really talking about symmetries in a spherical context. So there's a kind of deep theoretical parallel between angular momentum and spherical symmetry. And I just really wanted to mention that because, you know, this is a course on symmetry, and I'm trying to persuade you that symmetry is kind of pervasive across so many disciplines and so many different aspects of chemistry. And actually this is another one. When we look at subshells, in a sense what we're really looking at is symmetry characteristics. Now onto molecular orbitals. So this might seem like a bit of a jump, but actually we're going to see there's a big feature in common. So I think we might have seen this before, the molecular orbital diagram for oxygen. So up on the left hand side we see 2s and 2p. So these are the atomic orbitals in oxygen, and we can see the configuration there, S2p4, with those electrons indicated there in red. And then right in the middle of the diagram are where these atomic orbitals overlap. And so we've got a kind of pictorial representation of the orbitals overlapping. So with the 2s overlaps, you can see we've got these circles representing the s orbitals, and the shading represents the phase. We always think of the s orbital as being positive in phase, but really the main thing is that it's just the same phase throughout. It's kind of arbitrary whether it's positive or negative. And so in fact we can choose 2 phase combinations that are the same at the bottom or different at the top. And so these are labelled sigma. And of course we think of sigma as being head-on overlap between orbitals. And we can contrast that with the case above. And so this is involving the 2p atomic orbitals of oxygen overlapping. And we see there's 2 ways in which they can overlap. At the bottom and the top there, we've got the head-on overlap between orbitals, where in the bottom there the phases are aligned and at the top they're opposed. And so we give these, again, the sigma label, sigma for head-on overlap. And you see these G and U labels coming in as well now, referring to the symmetry when you reflect it through the centre. And of course an oxygen molecule has got a centre of symmetry right in the middle. So you can see that the bonding orbital between 2p orbitals is going to be symmetrical with reflection through the origin, and by contrast the anti-bonding one at the top is not going to be. But in fact it's exactly opposite. So when you do the symmetry operation, the lobes all land on other lobes, but all the phases have been reversed. And we see just the same thing in the s orbitals overlapping to form molecular orbitals, where we've got again the G and U labels reflecting the even and the oddness with respect to that symmetry element reflecting through the origin. And then finally, around the middle there, looking at the 2p orbitals overlapping, we've got the sideways overlap of p orbitals, and this is our definition of pi bonding. And so we can see that when you have sideways overlap where like phases overlap, that's a bonding interaction, lower in energy. Then we have the anti-bonding energy a bit higher up there where the phases are opposed to each other. But curiously in this case we see that the parity works out the opposite. So it's because of the different symmetry or the different orientations of the orbitals in a pi overlap arrangement, we see that the bonding arrangement is actually anti-symmetric with respect to reflection through the origin, while the anti-bonding is symmetric in that sense. And we also see that because we've got two p orbitals, if you like px and py, that can sideways overlap to form a bond, then we've got pairs of these orbitals shown where in the molecular orbitals, where the atomic orbitals are at 90 degrees to each other. That's why we get these pairs of pi orbitals. So, I mean, that's a reasonably standard look at this molecular orbital diagram. But what's quite interesting is the connection here between sigma and pi bonds, which we're familiar with, and s and p orbitals, which we're familiar with. So it may not have occurred to you that sigma and pi are the Greek for s and p. These are s and p translated, if you like, into the Greek alphabet. And that is quite significant when you think about it, because remember, the s orbitals, in symmetry terms, these were orbitals that had no nodal plane. And likewise, the sigma bonds, which we used to think of as head-on overlap, we could also define a sigma bond as a bonding orbital which has no nodal plane, just like we did for the s orbital in the atom. And likewise for a pi bond, where you've got the sideways overlap, we find in these cases, when you look at the picture here, you can see that each of these has got a nodal plane. And so, just like a p orbital has got one nodal plane, a pi bond has got one nodal plane. So there's a nice connection here between the atomic and the molecular symmetries, kind of the same in terms of nodal planes. And this is why I think you're basically using the same letters, but just using a different alphabet to distinguish between them. And so yeah, just a reminder here about the G and the U labels, and how they kind of go the other way when you move between sigma and pi bonds. And then just interesting thing that this diagram throws in is it also throws in this idea of a transition. And so in the ultraviolet and visible part of the spectrum, there's enough energy in the photons of light often to move electrons from one orbital to another. And so you can see that you've got two particular blue arrows in the picture here, and the longer one, the left-hand one, which is labelled E sigma. E sigma, this is the energy difference, because we've effectively got energy on a y-axis, haven't we, in this picture? So that E sigma, that's the energy jump to go from the sigma bond up to the sigma antibond. So the sigma bond has got electrons in it, the sigma antibond is empty, and it's possible to promote an electron from the bond to the antibond. And this will be a transition in an ultraviolet spectrum. And then on the right hand side there we've got the shorter blue arrow, and this is E pi, and so this is the energy gap between a pi bond and a pi antibond. We do have electrons in the pi bonds, but those pi bonding orbitals are not full, so there is room for them to take another electron being excited up from the bottom there. And in fact I'm going to talk a little bit about these ultraviolet transitions, because they do link in with what we've been talking about. And so there are some symmetry tricks we can use. The illustration on the screen here just shows us what's involved in ultraviolet visible spectroscopy. So we've got a light source, then using the prism or the grating, effectively we can divide that light up into all its different frequencies, and then we might put, for example, one frequency at a time through our sample in the solution there on the right, and we can compare the intensity of the light going into the solution with the intensity coming out, and therefore we can create a spectrum based on how much light is being absorbed. This is how our UV-Vis spectra work. And in fact, at a sort of slightly more technical level, what we see is a resonance between two electronic states in the molecule, resonating with the oscillating electric field in the light in the electromagnetic radiation. So that's the sort of what's physically happening in the transition. And so actually we need to look at this in a bit of detail, because it's typically the electric field rather than the magnetic field in electromagnetic radiation, which we're using in spectroscopy. There are some cases where the magnetic part is more important, but most of the time it's the electric field part. And so that electric field oscillation, we can think of it as an electric dipole vector. And actually this rather links into what we learn about bond dipoles. So if you have a molecule which is polar, like HCl, and you've got delta plus at one end, delta minus at the other end, we've got a separation of charge, and that separation there's a very distinct direction. That's to say, it's along the molecular axis, and so it's a vector quantity, because there's the magnitude of the charge separation and there's the direction of the bond, which is polar. And so it's a little bit like this when we do an electric dipole transition using light. The electric field is oscillating, and we treat it in the same way as an electric dipole vector. Now, this next bullet point looks quite complicated. It's meant to look complicated just to emphasize the point about how symmetry can simplify things. So if you're trying to work out how intense a transition will look in a UV-Vis spectrum, you actually need to solve an integral over all space, and it's going to involve the wave functions for the initial state and the final state that are connected by the electric dipole transition. And in addition, we also need a term in there for the vector representing the oscillating electric field. And so this can be mathematically extremely difficult, because we could have some very complicated multi-electron states, which could involve a lot of mathematical functions to describe. And we've got the product of two states and this kind of electric dipole vector, which we have to represent some way. So we could potentially have a horrendous integral to have to worry about. And this is the great thing about symmetry, because it can just cut through a lot of very difficult work. And in fact, this is what we can do with this idea of parity symmetry. It can save us a huge amount of effort here. And I'll come back to the picture on the right in a minute. So that integral, which I mentioned earlier, ultimately, if you solve the integral, it effectively gives you a probability of the transition happening. The probability is just a number. And so a number, just a pure number, because it's not a vector or anything, it's a scalar. There's nothing directional about it. And not being directional, it would by default have even parity. So we can get into our parity again. And so that means that the three things we're multiplying together, the wave function for the initial state, the wave function for the final state, and the electric dipole vector, when these things are all multiplied together, they're going to have even parity. If they had odd parity, then necessarily an integration over all space must cancel to zero, because odd parity means that, you know, exactly half of the function is odd and half of the function is even, if you like, and putting it slightly crudely, and then when you sum them together they cancel. So we have to have even parity when these things all multiply together. Now when you look at the electric dipole vector, because you've got plus at one end and minus at the other end, you know, it's a bit like an arrow. In fact, we depict dipoles with arrows, don't we? And of course these arrows are necessarily odd parity, because when you reflect them through the centre, the arrow is pointing in the opposite direction. A little bit like a p orbital was odd parity, same sort of thing, positive at one end, negative at the other. So we know that the electric dipole vector is going to be odd parity. And so we then have to consider what the two wave functions' parities are when we combine them. And so they combine, and it's a little bit like when you add numbers. If you have an even parity wave function and multiply it by another even parity wave function, the product is even parity. Odd times odd also comes out as even. But if you combine two parities that are different, then the product comes out as odd parity. And this is going to turn out to be very significant, because if the overall product of those three things has to be even parity, then it turns out that the two electronic states have to have opposite parity. So those two opposite parities, they'll combine to make an odd parity. And then the odd would multiply by the odd of the electric dipole vector, and then the final result is even. And that's what we require to see a non-zero result for our integral, for our transition probability. Oh yeah, just a slightly random thing I've just thrown in here. We spoke about pi orbitals as the sideways overlap of p orbitals. Well, you can have a sideways overlap of d orbitals, and actually this is what I've got reflected with those blue and yellow blobs there in that picture. They're like two of our d orbitals overlapping sideways on. And so I wonder if you can guess what sort of bond this is called. Because with d, we're up to now L equals 2. We've got 2 nodal planes now in this bond. So, as you might have realised, when you translate that d into Greek, this is actually a delta bond. And delta bonds are very exotic things, but you do see them occasionally in chemistry. And I've actually got a molecule depicted below which shows a delta bond. And it's this chromium species here, which has got a quadruple bond. So you see, normally we see sigma bonds as single bonds, don't we? And then you can have 2 pi bonds on top of that. So a triple bond would be a sigma and 2 pi's. And so if you want to get a delta bond on top of that, it's going to end up being a quadruple bond. So it's one of these exotic quadruple bonds here. Sigma, 2 pi's and a delta. Interesting one, that. So having looked at all this stuff about parity, we can see that the rules actually don't always hold. And in fact, one thing I would just say first of all is that when we're looking at the oxygen molecule, we had the you notice that when we went from sigma to sigma star, we were going from G to U parity symmetry, and when we went from pi to pi star in our transition, we went from U to G parity symmetry. So in fact, that was in accordance with these rules. We had opposite parity in the initial and final states, and that's what allowed the transition to be allowed. Had we had same parity between states, then we could predict that it would be a forbidden transition, which is to say we'd expect the integral of the transition probability to come to 0 because of the odd parity-ness of the product of the two wave functions and the operator. So that worked very nicely, if you like. It was nicely consistent with what we see in the oxygen molecule. And so now I'm going to jump ahead to where things go slightly wrong, where we see transitions despite rules being broken. So when you do UV-Vis spectroscopy on transition metal ions, we typically see transitions between d orbitals, the electrons moving from one d orbital to another, so-called d to d transitions. But the problem with this is that, of course, a d orbital has got even parity, and so when you go from a d to another d, they multiply up to give even parity, and when they multiply by the odd parity electric dipole vector, that would leave you with odd parity. So that would seem to be forbidden. And yet, despite that, we do observe colour in transition metals. And so this is a little bit troubling. How come we've got away with transitions when they break our parity rule? And this is because parity is only a thing, it's only relevant if you're in a symmetry where there is such a thing as the I symmetry element, that centre of symmetry. But if you're in a species where there was no centre of symmetry, then the whole thing just isn't an issue. There'd be no parity labels, and parity wouldn't even be something to think about. And so when it comes to how you can observe one of these parity rule breaking transitions, there are cunning ways that nature can get around this. And this can involve bond vibrations. So this example here I've got is considering, say, a copper ion in water. So if it's dissolved in water, you've got the H2O ligands surrounding the copper 2+ and effectively forming a bond. We sometimes think of it as a dative covalent bond between the ligand and the transition metal ion. And it turns out, of course, that once you start allowing bond vibrations, that's moving all these nuclei around, and so it could be that through the bond vibration that you lower the symmetry, and you in fact remove the centre of inversion through the vibration of the water molecules. You'd no longer have a perfect octahedral environment. Of course, the octahedron, being a platonic solid, has a centre of inversion symmetry, but of course if you change the lengths between the corners and the center of the octahedron, which would be like vibrating the bonds, if they're not vibrating in a symmetrical way, you could remove that symmetry element. And once that symmetry element's gone, the whole parity selection rule is gone, because you no longer have that parity label to consider. And so we end up in a slightly grey area, because there are in fact lots of these so-called rules or selection rules about whether or not transitions can happen. And so in a sense, as I say, a bit of a grey area. So some transitions can be more allowed or more forbidden, depending on, if you like, how well they behave according to these rules. You know, how many rules they break or follow, and how easy it is for the molecule to get around one of these selection rules. So it's all quite complicated. And so it turns out that these forbidden transitions tend to be visible but weak. So the system somehow finds a way to get around the rule, but it's never going to be as intense as if it hadn't broken a rule. So these selection rules are important things in spectroscopy. They effectively determine how intense transitions are. And I thought I'd finish with this fairly extreme case of colouring compounds, looking at potassium permanganate, potassium manganate 7, and the really extreme colour in this case, and say comparing it to something like copper 2+, which is quite a bit paler. And this can be understood in terms of selection rules. And of course the manganate ion is tetrahedral. And one of the things we learned about the tetrahedron, looking at platonic solids, it's the one platonic solid that doesn't have a centre of symmetry. So there's no parity selection rule to worry about in the tetrahedron. And also, sort of incidentally as well, we're not even looking at a D to D transition, because manganate 7 is formally D0. So actually the transition really is a so-called ligand to metal charge transfer, which means to say an electron from an oxygen atom from a p orbital there would move across into a d orbital effectively on the manganese ion. And so there's really no impediment in terms of selection rules to that transition, and so it's incredibly intense. And we have actually a problem when we use manganate solutions in chemistry. We normally use a 0.02 mol per dm cubed solution. When you've got that in a burette, you actually can't see the bottom of the meniscus because it's so intensely coloured. So it really is very intensely coloured, and some time ago we did a little study of this using our spectrometer. And in fact we had to dilute it down to something like 1,000th of a mole per dm cubed just in order not to saturate our spectrometer, which just goes to show you how remarkably intensely coloured it is. So in fact you can take that regular solution of the 0.02 mol per dm cubed solution we find in the lab, you can dilute that down 100 times and you can still see the colour. And in fact these pictures here on the slide were taken, they're actually from a newspaper article. This was a story that came out of Canada a few years ago, when there'd been some problem and some manganate accidentally contaminated the water supply. So it looks appalling. Everyone was horrified to see this bright pink water coming out of their taps. But ironically, of course, the concentration of manganate would have been pretty low. Still a cause for concern, but it just looks all the worse because of its intense colour there. It's kind of ironic because manganate is this extremely intense colour, and yet it's D0, and of course we often meet colour in transition elements in terms of a D to D transition. Manganate 7 doesn't formally have any D electrons, and it's still very intensely coloured. And another peculiar twist in all of this is Mn2 plus AQ. And so this one, which does have D electrons, you might expect this one to be coloured, but actually manganese 2 plus is so extremely pale, it's essentially colourless, despite the fact they're DD transitions. Well, of course, the DD, we have the parity selection rule, making the transitions a bit weaker, but of course we do normally see DD transitions. But there's something special about manganese 2 plus, and that is, here you can see, is that in the ground state here we expect to see the 5 electrons spinning parallel in the orbitals. So if you wanted to move a d electron from one orbital to another, that would require changing its spin, because you couldn't get 2 up spins in the same orbital. And yet there is a selection rule, a spin selection rule, which says you can't change the spin of the electron. And so in the case of element 2+, this is extremely pale because it runs into two selection rules. You've got the DD parity rule and the spin selection rule. And so this reflects how very pale it is. And so there's this idea then that, you know, the more selection rules you break, the more forbidden the transition, the more weak it becomes. There we go. So we've just hit 40 minutes, so I think we'll leave it there.